Assuming your data are a good multiple sequence alignment, then your next step is to calculate the neighbor joining tree. Choose the MEGA window and click on the phylogeny button. This will bring up a menu of analysis options. To build a neighbor joining tree, choose Construct Test Neighbor Joining Tree. This brings up the Choose Data File to Analyze window. Navigate to the MEGA format data file you just created and choose it. This brings up the M5 Input Data window. Choose the appropriate data type from the list and click OK. If your data are DNA, a window will pop up asking if your data are protein coding DNA sequences. If they are, you will then be asked to choose the appropriate genetic code. In this example, we are using nucleotide sequences and they are protein coding. And we are going to use the standard genetic code for these data. This brings up the M5 Analysis Preferences window. Here is where you set your analysis parameters for the neighbor joining tree. Going down the list, the first parameter you will need to change is Test of Phylogeny. This option is where you choose whether or not to perform a bootstrap analysis. Because the neighbor joining method has no inherent clade support measure, you will always need to perform a neighbor joining bootstrap analysis. Typically, 500 replicates should be sufficient to get a good estimate of how well your data support the groups in the final tree. So for example, our options in Test of Phylogeny are None, Bootstrap, and Interior Branch Test. And we're choosing Bootstrap, and then that will bring up a window here for number of bootstrap replications, and we're going to input 500. Next, use the Model Method menu to choose the substitution model used to calculate the pairwise distance matrix for your analysis. Make sure the model that you choose is appropriate for your data. So we go down to Model Method, and there are several options here, from something as simple as counting the number of differences to calculating p distances, which is the number of differences divided by the length of sequences. Then there's the very simple Jukes-Cantor substitution model, the more sophisticated Kimura 2-parameter model, and moving on in sophistication as we move down the list, Tajima-Ney model, Tamura 3-parameter model, Tamura-Ney model, and then maximum composite likelihood. We're going to use the Kimura 2-parameter model. Now, looking further down the analysis preferences, you also have the option to choose whether substitution rates can vary among sites or are uniform. If you choose that they vary, MEGA will use a discrete gamma distribution to model rate variation. For gamma distributed rates across sites, you will need to supply the gamma distribution rate parameter. So in this example, we've chosen gamma distributed rates across sites. Our other option is to have uniform rates. And in the window below, we've input the value of 2 for the gamma shape parameter. This value of 2 is a good estimate for data that are not exceptionally divergent. Once our parameters have been set, then we will click on the Compute button to run the analysis. When the analysis finishes, it will open a Tree Explorer window, which will contain an image of the original tree. If you ran a bootstrap analysis, there will be a second tab in this window containing the bootstrap consensus tree. Now, as we see from this example, both the original tree and the bootstrap consensus tree contain bootstrap percentages at interior nodes. However, bootstrap consensus tree collapses branches that have lower than 50% bootstrap support. So we see a different topology in the bootstrap consensus tree versus the original tree. Both tree figures will have these bootstrap support percentages on the internal branches of the tree. The Tree Explorer window has several options for formatting your tree figure, which can be invoked using the buttons running down the left side of the window. The second button down is the tool used to reroute your tree figure. To do this, click on the button. This will change the cursor to the reroute cursor, Place the arrowhead on the middle of the branch where you want the root to be and click. So in this case, I'm going to change the root to be on the branch leading to sample 6 and sample 7. This will change the tree root to this location that was chosen. The next button down is the Flip Subtree tool, which can be used to rotate an internal clade around its basal node. This does not change any information in the tree, but can make the tree look better. Now in this case, I pretty much like what I've got, but as an example, I'm going to flip this internal group here to put sample 1 up on top, followed by 2, 5, and 4. And I can likewise go back one more and put sample 3 on top if that's what I like. Other tree formatting options are available through the buttons running along the top of the Tree Explorer window and the menus above the buttons. These include a tool for generating a figure legend for your tree. When you click on this, a new Tree Explorer window opens up, and a figure caption which includes relevant information about the substitution model used for the analysis and the bootstrap analysis, among other things. So we choose caption, and there is our generic figure caption for the analysis we just performed. Back in the Tree Explorer window, the last thing you will need to do is export your tree. You can export the tree in a Newick format text file using the Export Current Tree Newick option in the File menu. You can export the tree figure as an EMF, TIFF, or PDF formatted file using options in the Image menu. And there you have an example of how to use the program MEGA to generate a neighbor joining tree and export the tree figure from your analysis.